Hello, this is Module 5 of Graduate Statistics, University of Cincinnati, and we are on video lecture 3, continuing with the guided activity. All right, so we had just printed the contingency table that we needed to start making sense of the data and answering the question at hand. And in question 4, I ask you to write a command to visualize or print the table. So pause it and give it a shot. So as you can see, the contingency table was assigned to an object called contingency table, and you can call it out to print just by typing contingency table. That's all you need to do to print it out and visualize it. All right, now we don't see the totals in the table. It would be nice to have those, just like we had it on the slides. And we can do that simply by using the function add margins, which and margins comes from, these numbers come in the margins, the sums. And this function takes as input the name of the table, the name we gave to the table, or the name of the object that's storing the table. So try it out. I hope you paused the video and you're ready for the response. So here we would do add margins, and we would put the name of the table inside, which is contingency. And if we do that, boom, we have the sum. So we had 24 supervisors that received a female file, 24 that received a male file, so that works out fine. And then we had 35 promoted and 13 not promoted. So we have all the information that we need right there to start computing interesting statistics. Now in question 6, I'm asking you to pause the video and take some time to interpret the data. What is the data telling us? So given our question, we start with the question in our head. Given the question that we're asking about gender discrimination, the data is consistent with a bias against females in promotion decisions. Why? Let's look at the promoted column to extract this idea. So we had 14 females out of the 24 being promoted, compared to 21 out of the 24 being promoted, right? So the data is consistent. It's not sufficient for us to conclude, as I already alluded to during the slideshow. It's not sufficient for us to make a conclusion, but it is consistent with the conclusion of gender bias because you have more males being promoted than more advisors promoting the male file than the female file. So type the answer there because you're going to have to hand this in. And now we have to extract from the contingency table the summary statistic that we would like to be able to compare the promotion decisions. And of course, here you have raw numbers, as I said, you had 14 versus 21, but you would like to use a standardized metric that could be compared across studies that had different number of managers, right? So a seven difference, right? 7-point difference might not be as bad if we had 100 supervisors making a decision about the female and the male files, right? Because in proportion, it would not be that large. But if we are on a universe of 48 advisors only, then it might become more significant. So we want a number that's not affected by that. So proportions would be good. So think about question 7. What sample statistics should I take from this data to summarize or capture the essence of this story this table is telling us about promotion decisions. If I need one number, what would this number be? So if you paused the video and you're ready for the response, then listen up. So the summary metric I could compute is I'll take the proportion of females that were promoted, 14 divided by 24, the proportion of males that were promoted, 21 divided by 24, and subtract one from the other to get the difference in promotion decisions in percentage. Percentage difference in promotion decisions would be the sample statistic of interest, right? So here's the relevance contingency table again. And let's compute then the sample statistic that we just mentioned before. You have in the step 1, we're going to compute the percent promotion decisions in the female group, and that's 14. Oh, let's put the totals in there. And that's 14 divided by 24, so that's there. And I'm assigning that ratio, that percentage, proportion, to promoted females. And then I'm computing the percent promotion decisions in the male group. So that's 21 divided by 24. That's a proportion. If I multiply by 100, we get the percentage. In step number 3, I am computing the difference between promoted males and promoted females. If I have a positive number, that means there's more promoted males than females. And that would be consistent with a bias against females. If I have a negative number, then it would be consistent with a bias against males. So if I run all of this, the first number, as we saw in the slide, about 58% of managers decided to promote the female file. About 88% of the managers promoted male files. And step number 3 is the difference between the two, and that's around 30%, 29%. Okay? All right. So the results show that the group of supervisors that received the file marked as male decided for promotion more frequently than the group of supervisors that received the file marked as female. Therefore, a gender-biased difference in promotion decision there was therefore a gender-biased difference in promotion decisions of 29%. So that's this thing. Or we can round it off to 30%. All right, or approximately 30%, right? Guess good? All right, so let's move on. We ended the slideshow with the following question. Is a difference of 30% in promotion decisions for a male and female candidate observed in the sample sufficient evidence, because it was observed in the sample? We only looked at decisions made by 48 supervisors, randomly assigned in 2 groups. But we want to make conclusions about gender discrimination in the population of all managers. So here's the question. Is a difference of 30% in promotion decisions for male and female candidate observed in this sample sufficient evidence for us to conclude that there is a gender discrimination out there in the real world affecting all managers, or managers in general in the real world? Answering questions using data requires us to make that kind of inference, and that is what I mean by statistical inference. Inference from data to real world. So this is one of the learning outcomes. You need to know what statistical inference is. So I'm seeing a difference in the sample. Is this difference sufficient for me to conclude that it's likely that there is a difference out there in the population? In particular, we have to be pretty confident that this magnitude of difference in the sample did not just happen by chance before we assume gender discrimination is at play. Remember, People are innocent until proven guilty. That's the logic of statistical testing. We hold on to the idea that nothing is going on until we have sufficient evidence to dismiss that hypothesis. Statistical analysis is the best way we have at hand so far to ground our inferences. So now, on to new material, general introduction to inferential statistics. So I hope that so far you understood that description is a good start. We can see that there is a difference that is consistent with gender bias, but we need one step further. We need to think about whether this is indeed something that is likely to be happening on the population of all managers, right? So a general introduction to inferential statistics. Let's define data as patterns arising from systematic observation of a phenomenon. So here, that study on gender discrimination created conditions for us to systematically observe what happens about the promotion decisions, when there is only one difference between the candidate, which is the gender. Patterns in data can be a particular percentage difference in a decision, choice, preference, index between groups of people and or different places and or different periods in time, just like last data problem we worked with, or between conditions of interest. B, it can be a difference between means and medians of a variable between groups of people, places, periods of time, or conditions of interest. And C, a particular magnitude of correlation between two variables of interest. All of those things are patterns, right? Percentage difference, differences in means and medians, and also particular magnitude of correlation. In the gender discrimination example we're working with, data shows a difference, that's the pattern we're seeing, difference between the promotion of the male and the female file, right? When scientists are faced with a particular pattern in the data, with the ultimate goal of telling a story with the data, they have to initially contemplate two possibilities. So that's the process of making an inference. First thing, we have to set up some hypothesis. And there are two hypotheses that need to be set up. The null hypothesis, which says nothing going on. In this case, this translates to promotion and gender are completely independent. They're not related things. That is, there is no gender discrimination. Observed difference in proportions of 30% simply due to chance. And then we have the alternative hypothesis, which is, in a very general sense, there is something systematic going on here that is creating that pattern that I'm seeing. In our case, promotion and gender are dependent or correlated. Promotion decisions are gender-based. Observed difference in the proportion of promotion decisions for males and females is not due to chance. That 30% is likely strange enough that it makes us think that gender bias is going on. All right? Now, before we go on, I'll leave you at the end of this video with a question to think about, and the next video we will address it. Why in the world should we contemplate the null hypothesis if I'm looking at a difference of 30% in promotion decisions in my data? And in order to answer this question, let's consider the following scenario. Let's entertain the possibility that the truth is that supervisors in the real world are not influenced by a worker's gender when making promotion decisions. If that's the case, what should be the difference in promotion decisions made by supervisors that receive a male and a female marked file? Let's end here with this thought. If the truth is that there is no gender bias, what should be the difference between these decisions instead of 30%? What should it be? Think about this and we'll come back and address that question. See you soon.